Hey guys, welcome back to another low-level learning tutorial. In today's tutorial, we're going to be doing one of my favorite things when learning a new assembly language, which is going to be on the left, we're going to write some C, some very simple C, right? And we're going to do some basic things in C, like set some variables, set some string pointers, do some array assignments, function calls, stuff like that. And then we're going to compile it on the left, and then on the right, see how it translates into assembly and use that process to learn the assembly language that it creates. So this is the output of the binary, and there's a lot of code here that for the purposes of this video to learn the assembly we really don't care about. All we need to do is type slash for search in less, look for main, and it's going to be the first, second, third, fourth entry, okay? So this is the object dump output saying this is the address of the binary where main, the function, exists. And then everything south of that is the assembly language for the function main, right? So there's a lot that has to go on for a function to happen in assembly. We're not going to talk about all of it. We're going to talk mainly about what's going on to make these variable declarations happen, right? So when we're doing this, what I like to do is look for things that I call reality anchors, right? And a reality anchor is something that we have this chaos, right? This assembly language that we're not really sure where to even start. If you're new to assembly, this looks completely foreign to you. A reality anchor is a thing in our code that we know has to exist in the assembly. For example, we set the variable x equal to 1337, right? To me, I know that the number 1337 has to occur in my code. It is impossible for it not to. Otherwise, the code wouldn't be doing what I told it to do. We're going to look for 1337 to give us kind of a starting point to figure out where we should start to care about the assembly. And pretty quickly, we see this 1337 pop up, right? This is object dump telling us that hex 539 is decimal 1337. So then we're going to walk through this code and figure out where the thing that we've created goes, right? So, okay, so we look at it and we see, okay, it puts our number 539 into W0. And if you've watched my previous ARC64 tutorial, you remember that W0 is the lower 32-bit half of X0, which is just a working register in ARC64, right? It's just a register where you can do math in. And then it stores W0 at X29 plus 20. And remember, when you see these curly or these hard braces in assembly, that's a memory operation, right? You're saying treat X29 as an address and add 20 to it, and then put W0 at that location. So what that says to me is that X29 is being treated as some kind of stack pointer, right? And you're like, okay, no, the stack pointer is actually a separate variable, and that's true. In ARC64, they have two stack variables, or stack registers. One is called SP, and one is called FP, or the frame pointer, and that's X29. And what's happening here is it's saying treat the 20th index on the stack as the variable X. Okay, so we've figured out now how does ARC64 do decimal variable integer assignments. Right here, it takes the variable, it puts it in a working register, and then it puts that working register on the stack. Pretty cool, right? So we're kind of starting to figure out how the first line of assembly, or the first line of C rather, translates to assembly. Awesome. So let's move on to our next assignment. So we say that we have this pointer S, and this pointer S points to a string called hello world. Okay, let's see how this works. So we've already done the storing of 1337. Next we do this little number here, right? So we move 0 into X0. So that means that X0 is 0 at this point. We add this number here, interesting, to X0 and store that in X0. And typically, if you're not used to this, right, when you see 3 operands in assembly, it means perform the operation between these two and store it in the third, right? So we're saying this number plus X0 stored in X0, right? So that means that at this point, because this was set to 0 before, X0 is equal to this value. And then just like up here with our 1337, we're storing X0 onto the 24th index of the stack. And you may be confused. You may be like, where is hello world, the string, occurring here? Well, when you actually write hard strings like this in C, what happens is that string gets put in the data section of the binary at compile time, and every reference to it is actually treated as a pointer. So this pointer 98A is the pointer into the binary where hello world lives. So now at the 24th index on the stack, the variable s points to our string, right? Pretty cool. So we've figured out now how pointer assignments work in ARC64. It's very similar to integer assignments. It's just instead of the hard integer value, we get the pointer value instead, right? We're working through it. So next, in C, what I've done is I've made a variable called buff. It's a character array of 4 characters, and I set the character array equal to A, B, C, and D. So if we go back to our process, right, we need to figure out how does A, B, C, and D appear in the binary? Well, the way that I would look for A in the binary is by looking for its decimal value, which is 97, right, or hex 61. And you can see pretty quickly here, hex 61 appears, 97 appears, and it's stored onto the stack the exact same way that our 1337 was, right? We move it into a working register, and then we store that working register onto the stack. And now we know that the base of our buffer is at index 32 on the stack. And so we put A at 32, B at 33, C at 34, and D at 35, right? So we just did that entire array assignment in a matter of like 8 instructions, right? That's pretty awesome. So now it's going to get a little more complicated because we're going to do this loop. And what this loop does is really straightforward in C. It's just we have some counter I, set it to 0, and while I is less than 4, printf the hexadecimal value of buff I++, right? And all that's doing is it's printing hex 61, hex 62, hex 63, and hex 64, right? So we need to figure out how does it set up that counter, and how does the function call get set up for this loop to occur in the way that we told it to in C. And we can see pretty quickly that after we do our last assignment of buff, which is D, right, we set up this line here. And so when you are reading assembly, and if a register ever has a Z in the name, you typically can assume that that is some kind of 0 register that will always contain the value 0. And in ARC64, WZR is the working 0 register, which means that it will always contain a 0 value. So we store the working 0 register at x29 at offset 16, okay? And that means that variable I, which we set to be 0, is at location 16 on the stack. So keep that in mind, right? When we're talking about our counter I, we're talking about index 16 on the stack. That's where I lives. Okay, so we set its initial value onto the stack. Then we branch. It's not conditional. There's no conditions here. We always branch. So we branch AC4, which is main plus 80. So let's go to AC4, this line. We'll scroll down a little bit. Okay, so we load register located at x29 plus 16. So what is that? Think about it for a second. That's our variable I. We put I into W0. Compare I to 3. Interesting. And then branch if it's less than or equal to 3 to A9C. Okay, cool. So what we've actually just executed is our while loop here, right? This is the condition that we've set for it to iterate over. So we said while I is less than 4, the assembler did a little bit of optimization for us, and instead of I is less than 4, it says I is less than or equal to 3. It's the same logic, you know, it's just they made it probably a little faster at the machine level. So if it's less than or equal to 3, which in this case at our first iteration it is, we go to A9C, which is here. So then we load I into W0 again, right? So W0 is I, which is still 0 at this point. We add 1 to I and store it into W1, and then store that into i's location. Okay, so this is where we do I++, right? I++ is happening right here. So then we do SXTW, okay? Another assembly trick. When you see an X in an operation, typically what that's going to be doing is called sign extending. And the reason why we're doing a sign extension here is because we said that I is an integer, and we didn't say it was an unsigned integer. We said it was a signed integer. So what it's doing is it's expanding I, which lives in the 32-bit W0 register, and it's expanding it by its sign all the way out to X0. And then what do? We add 1 to, we add 20 hex, note that, that's important, 20 hex to X29 and store that into X1. Okay, so this is going to be a little bit of a trivia thing. I don't like how ObjectDump displayed this, but what is hex 20 in decimal? Hex 20 in decimal is 32, and where does 32 appear in our code? 32 is the base of buff. Remember that? That's where A lives, right? So this right here at this point, X1 will contain the base address of buffer, right? Okay, stay with me here. So X1 is the base address of buffer. We add the value of I before its increment. We add the value of I before it gets incremented to X1, so it's buff plus I minus 1 at this point into W0, move W0 into W1. So at this point, W1 is going to contain whatever character we're on, right? And then eventually we set up the format string, which is another string pointer in the binary for this string, right? And we put the character into W1, and then we call printf. Once that's done, we do the loop all over again. We load I off the stack, we compare it to 3, and if it's less than or equal, we go all around again, right? It's kind of cool how you can take what you know is supposed to happen in C and read it in assembly to figure out how the assembly language works at a very, very low level, right? So then finally, once we've done this 4 times, we go to this compare again. I is no longer less than or equal to 3, so we move on. We move 0a, or 0xa rather, into W0 and call putchar, which is happening here in our last line. And then finally, we move the return value into W0, which is where in ARC64 the value is returned. It's an X or W0, and they're both the same register. And then eventually, this is all some voodoo where we're checking the stack cookie on the stack to make sure it wasn't corrupted, which is protecting from buffer overflows. And then we return, right? So what we've done here is we've taken what we know is supposed to happen in C and figure out how that happens in assembly after the compiler has done its job. I hope you've learned something from this. If you want to see me do this with other C constructs or other assembly languages, drop a comment, leave a like, subscribe, let me know. Anyway, I hope you guys learned something and enjoy the rest of your day. Have a good night. Bye-bye.